Module 3.2, Theoretical Foundations of Molecular Dynamics. In this module, we will provide an overview of MD, an important component called force fields and their different types, challenges for performing a molecular dynamic simulation, and opportunities available. So in a typical MD, what we have, very similar to what we did in density functional theory, is first we decide the system that we want to simulate and atomic structure, such as for aluminum or for polyethylene and so on. Then we provide or calculate masses and forces are acting on the particles. And these forces are parameterized or fitted to density functional theory or experiments. This is how we establish a connection or coupling between DFT and MD. The DFT based data set is used to train or fit a model for smaller systems. And once that force field or model is developed, we can use that to guide very large scale molecular dynamic simulations. During molecular dynamics, after we fix the atomic structure, we can initialize position and momentum or velocity. And then we can solve the Newton's equations, which is we discussed in the last module, force, mass, and acceleration relation, to determine the position r at time t, velocity at time t, using the integrator method. So remember, we talked about the differentiation and integration in the mathematical foundation. So we're going to use some of that. And usually the time is a continuous quantity, but here for computational reason, we'll be solving them in the discrete region, that is non-continuous region. And once we have solved this position as a function of time, given a particular force or force field, we can compute important properties. We'll discuss about that, and we can estimate errors. And we can try to use such kind of simulation, kind of mimic the reality and answer physical questions. So this was first proposed by Elder and Wainwright in the University of California Radiation Lab in 1957. So I think this lab is now called Lawrence Berkeley National Lab, very famous national lab. And here on the left-hand side, I show you a molecular dynamic simulation of aluminum being pulled off. And then you can see after certain time, it actually breaks into pieces once you provide the tensile strain and so on. So one of the very important concepts in molecular dynamics is interatomic potentials, also known as force fields. So usually in solid state domain, people call it interatomic potentials, but in polymer and macromolecule regime, they call it force field, but they are kind of the same things. So interatomic potentials are mathematical functions that describe the potential energy between the atoms or molecules as a function of their positions. So this is very similar to what we learned about the exchange correlation plus the Coulombic interaction and so on in density functional theory. So there it was being computed from scratch or from ab initio. Here we have to give a fitted potential. So this is what is makes force field kind of dependent on density functional theory or any other experimental data. So these potentials and their accuracy are very important for determining the force in MD simulation. So if your potentials are not good enough or not accurate enough, so you'll get very erroneous molecular dynamic simulation. So before performing any molecular dynamic simulation, it's a good idea to benchmark this compared to experimental data, validate this, some of the properties such as the lattice parameters, bulk modulus, elastic constants, radial distribution function. Some of this property, we'll talk about that in coming few slides. And once we have verified that, then only it's a good idea to use that MD with some sort of confidence for performing molecular dynamic simulations. And these force fields are also different types. So there could be pairwise potentials, that is two body. So on your right-hand side, I can show you there are two blue balls connected with a spring here. So this is kind of two body interactions. And these are simplest forms. So it considers only the pairwise interactions. And very famous example is Lennard-Jones and Coulombic potential. So Coulombic potential we have seen in our undergrad Q1, Q2 over R potential. And Lennard-Jones is another sophisticated 612 kind of potential. We'll try to discuss and solve one of the Lennard-Jones potential for one-dimensional system, as well as using commercial software, software such as LAMMPS. So these are pairwise potential. These are extremely primitive, very rarely used for engineering applications. What is used is many body potentials. So we can, in that case, we consider not only two body, but we also consider many bodies, so three body, four body, and so on systems. And it can provide more accurate representation of atomic interaction. So some of the examples are embedded atom method, EAM, modified embedded atom method, MEME, Tirsoft potentials, and so on. And there could also be bonded potential and non-bonded potentials. Potential which use angle, torsion, and some which do not, and so on. So luckily, there are a lot of documentations about these potentials, and we will talk about some of them briefly in this module. So as I said, there are different types of force field, and you can kind of classify them based on what kind of information they are using inside them. So they might be using only bond, or bond plus angle, or bond plus angles plus dihedral, which is a four body, bond plus angle plus dihedral plus improper. That's more accurate. And if you consider electrostatics plus van der Waals, then it becomes more accurate. But again, the challenge is parameterizing more complicated potentials can be very time consuming and extremely tedious tasks. So we will try to stick with some of the simpler potential in this tutorial. You can find more details about this if you have this book on fundamental of multi-scale modeling of structural materials. Feel free to check it out, the chapter on MD, but it's not super recommended, but it's just a suggestion. So these are some of the commonly used force field for molecular dynamics, or they are also used in Monte Carlo simulations. So such as CHARMM, which is used for organic molecules, AMBER for biochemical molecules such as proteins, nucleic acids, Druiding potential for polymeric and biological systems, OPLS, biological or macromolecular systems, CFF, REACTS-FF for metals, ceramics, silicons, polymers, clay-FF, and so on. So what are the challenges of using force fields? So first, as I mentioned, and I want to emphasize it more, that it requires extensive parameterization. So sometimes students spend their entire PhD to develop one force field. So that's like very typical. At least a few years ago, that was the case. Unless we have the machine learning or some modern techniques. The conventional way of developing force field is extremely challenging, and that makes the force field or molecular dynamics very difficult to model a general system. And also, they require high-level quantum mechanical data, such as density functional theory data, to parameterize. So these quantum mechanical calculations that we learned from the previous tutorial can also be time-consuming. So they are also not transferable. Very similar that we had for the density functional theory case. The same GPAW code was used for aluminum, nickel, nickel aluminum, carbon, and so on. This is not the case for force fields. So something maybe for aluminum, something maybe for carbon, but it might be for both nickel and carbon. So these are the flexibility limitations that are important to understand before we actually run more molecular dynamic simulations. And also, as I said, how we represent non-bonding interactions. So Coulombic and van der Waals bonding in molecular dynamics could be extremely tedious. So especially if you are dealing with carbon-hydrogen compound, then you need to include van der Waals interaction and so on. So this could be also an important feature to look into. And of course, it doesn't have electronic properties such as density functional theory. And as we scale it up, we have more and more complex features that we might need to capture, such as bonding and non-bonding situations, different chemical environments. And as we simulate larger systems, we will run into computational cost as well. So how do you overcome these challenges? One of the approaches, especially for combining classical force fields with quantum mechanical principles, were developed by Martin Karplus and co-workers, for which they were given the Nobel Prize in 2013, and that is one of the approach. A new type of approach has also come along. So this is development of new type of force field based on machine learning. So here, instead of fitting data using manually used techniques such as simulated annealing and so on, we'll be using machine learning to automatically establish the relationship between the MD and DFT, right? So I have been quite active in this field. So we recently published an article of unified graph neural network force field for the periodic table, so it can kind of simulate anything in the periodic table up to 89 elements and their combinations. And hopefully during machine learning module of this course, we'll be able to talk about that a little bit.